Let us take we will speak some questions, very simple questions. Let us try. Suppose we are having here a question as x bar, y bar, z, x, z, y, z. Let us take the question as the number of logic gates required to realize the given Boolean expression. Let us take the question as the number of logic gates required to realize the number of logic gates required to realize the given Boolean expression. Suppose we are looking to the options as say 0, 1, 2, say none of the above. None of the above, suppose. If it is a question. So to identify the number of logic gates required to realize the given Boolean expression, default, whenever we are having a question, we have to try for minimum gates. That is the default understanding. We must try for a minimum number of gates. The default case, whether it is mentioned or not mentioned also. Sometimes you will be having the question description that will be mentioned the minimum number of gates. Sometimes you will be having a question. You will be having a question as the minimum number of logic gates required. If it is mentioned, well and good. If at all it is not mentioned also, you have to try always for minimum number of logic gates. To identify the minimum number of logic gates, we need to simplify the given Boolean expression. In the given Boolean expression, we are having possibility to take z as a common. We are having possibility to take z as a common. If you take the z as a common, the expression is x complement, y complement, r with x, r with y. Among these first two terms, using distributivity, we are having possibility for the simplification. If you simplify properly, it is y bar r with x. If you try well properly, the result will be y bar r with x. We are having here, this is x bar, y bar, r with x. Using distributivity, we are reading this as x r with x bar and with x r with y bar. In the fourth property, it is 1. 1 and with anything is anything. Anything is x or y bar. Hence, directly with the practice, you must be in a position to read this result. Using distributivity, we are having possibility to read this result is to be x or with y bar. And of course, this y is as it is. And with the z. We are looking y or with y bar. The group of these two, it is 1. That is the fourth property what we are having. It is the fourth property what we mentioned. And using third property, using third property, 1 r with anything is 1. So we are looking here, it is 1. So effectively 1 r with x. So 1 r with x is only 1. On the whole, this total thing is resulting. On the whole, this total thing you can replace as simply 1. So z and with 1 will be z. So once it is a result from the given options, the answer must be option A. We are not in need of any logic gate. So when we are having a question of this nature, when we are having a question of this type, to read this result, we are in need to use these properties. We are in need to use the properties. So like this, the usage of the properties we are having. Let us try for one more question. Simplify the given Boolean expression. A, B bar are with A, B, C bar are with A, B bar, C, D. The simplified expression of the given Boolean expression. Again, let us consider some options here as A complement B or C. Option B, A and with B complement or C complement. Option C, A complement and with B complement or C complement. Option D, none of the above. Suppose we are having a question something like this. So we are looking here, the expression is having total 3 terms. The expression is having total 3 terms. Among the first term and last term, we are having possibility to take AB complement. A and with B complement is a common. So when we are reading A, B complement as a common, within the parenthesis it is 1 or with a CD. And of course, second term, let us write as it is. We know from the third property, 1 or with anything is 1. Effectively, it is only A, B complement. And of course, this term A, B, C complement as it is. Here, we are having possibility to take A as common. While taking the A as a common, within the parenthesis, in the bracket, that the parenthesis, we are having B complement or with B, C complement. Here, by using distributivity, possible to read as A and with B complement or C complement. You can check by using distributivity how we are working on this in this bracket. B complement or with B, C complement, this will be B complement or B and with B complement or C complement. This B complement or with B is 1. So 1 and with anything is anything is B complement or C complement. So it is the simplification what we are having. The question what we took is the simplified form of the given Boolean expression. We are having a question, a simplified form of the given Boolean expression. Simplified form of the given Boolean expression. So answer to this question for the given options we check, the answer is option B. So again, to work on this question, we need to use the Boolean algebra properties. With the knowledge of the Boolean algebra properties, we are having the work on this question. So we are able to speak the answer as option B. So like this, we are having the usage of the properties. We can make many questions of like this. We'll see later. Let's come to the listing of these properties. AB R with A complement C R with BC is equal to AB R with A complement C. It is also one of the important property. What is the importance of this property while looking to the equation itself possible to recognize? With all this work, basically our interest is minimizing hardware cost. With all this sort of mathematical work, our interest, our concern is to minimize the hardware cost. Hardware cost of any digital system or any digital circuit will be minimum whenever the Boolean expression or equation what we are using to realize the circuit, that Boolean expression or equation is having the lesser number of terms, then definitely by using that expression, if you realize the circuit, the cost of the logic circuit will be less. If the property is true, we are recognizing RHS expression is having 2 terms, whereas LHS expression is having 3 terms. If the property is true, if you use RHS expression, definitely the cost of the logic circuit will be less. We can understand based on our discussion. For realizing LHS expression, we are having here in need of 3 AND gates, because 3 terms we are having among those in the terms among the variables we are having AND operation. So the 3 AND gates are required, and of course 1 OR gate is required. Don't speak as 2 OR gates. It is only 1 OR gate. But of course, OR gate we need with the 3 inputs. In the regular class, normally scenario, when we are putting this as a question, students used to answer 2, because you are fixing the idea the gates are with only 2 inputs. With that idea, you will be answering as 2. The reason is 2 OR operation we are having. It is not the case. In the beginning of the discussion, I said already, the gates are available with more than 2 fan-in, more than 2 inputs. No doubt, 2 input OR gates are, if at all we want to use, then 2. But if 3 input OR gate is available, then we will be using only 1 gate. Hence, we are in need of only 1 OR gate. Our gates are available with any number of inputs. The gates are available with 5 inputs, 10 inputs, even 20 inputs. Gates also available. So on the whole, we are in need of here 4 gates. If the property is true, with the RHS expression, if we try the logic circuit, we are looking here only 2 AND gates, and of course here also only 1 OR gate. It may be 1 OR gate, but the cost of this OR gate will be less. The cost of this OR gate is less comparing to this gate. That discussion we already had. The reason is, here the gate fan-in is 3. In this case, the fan-in for the gate we need only 2 because of 2 product terms. As and when the gate is having, the fan-in is less, the cost of the logic gate is less. On the whole, we are looking the importance of this property like this. If at all this property is true, with the knowledge of this property, whenever we are having in the given expression 3 terms with such sort of relation, those 3 terms we are having possibility to replace with only 2 terms. Can you speak what is the name of the property? Can you guess what is the name of this property? The name of this property is consensus property. It is also named redundancy property. Redundancy property. It is also named as a redundancy property. Why we are naming as redundancy property, I will speak little later. Let us try to look to the proof of this property with the conventional algebra approach. In the conventional algebra approach, as we know, we may start with the LHS expression or we may start with the RHS expression. Suppose if you start here with the LHS expression, the LHS expression is AB or with A complement C or with BC. So with some mathematical manipulation, we will try to look now, this is to be RHS. Hence, to simplify this, BC, the last product term, let us take AND operation with 1. We know Based on the second property, 1 AND with anything is anything. So if at all BC AND with 1, logically it is not going to disturb. Later, this BC AND with 1, what we are looking, 1 we are having possibility to replace using fourth property as A or with A complement. Using fourth property, this one we can replace as A or with A complement. So if you do this, this is A or with A complement. While expanding this, this is AB, it is A complement C, it is ABC, it is A complement BC. From the first and third term, we are having AB is common. While taking AB is common within the parenthesis 1 or with C later. While taking A complement C as a common among the second and last term, we are looking here A complement C and with 1 or with B. From the third property, we know 1 or with anything. 1 or with anything is 1. And from the second property, we know 1 and with anything is anything. Anything is here AB. Whereas anything is here A complement C. So it is a result what we mentioned here. Now let me speak why we suppose name this consensus property as redundancy property. Redundancy for what? Redundancy on which term? If that is a question. The LHS is having 3 terms, RHS is having only 2 terms. So what we are looking is, if you name the first term, second term, it is the third term. We are having elimination of this third term. So this term we can name as redundant term. The third term we can speak as redundant term. Based on this, we are naming this consensus property as redundancy property. Try for the dual of this consensus property. Try for the dual of this consensus property. It was a question very long back, of course, 22 years back. 1998, it was a question, redundancy property. The dual of this. It was a great question. So if you look here, dual of this redundancy property or consensus property is A or B and with A complement or C and with B or C is equal to A or B and with A complement or C. So once it is a dual of X, no need to see separate proof. Default the proof of X is valid for this dual. X or Y and with X bar or Z. Try what is the result of this expression. So if you look to this, the result of this I asked, the result of this by using the consensus property possible to read as XZ or with X complement Y. To work out here, let us expand the LHS. So LHS is X or Y and with X bar or Z. So this will be X complement or with XZ or with X bar Y or with YZ. This is 0. Now among these 3 terms, we are having possibility to use the consensus property or this redundancy property. If you look to the redundancy property, let us name one of the term as the first term, or we can name as a reference term. Suppose if I name this a first or say reference term, In the same expression, if you look the second term, one of the variable must be complemented. And second literal must be new from the first one, second literal. If that is a case, if such a second term is identified, in the same expression, if you look at term which is coming from the first two terms, second literals, the third term is redundant term. The third term we can eliminate. It is observation. So based on this, what is the conclusion? The redundancy property or the consensus property possible for us to use among the three terms, but among any three terms not possible for us to use. Suppose I am having a expression something like this: xy, r with yz, r with xz. Suppose here also I am having three terms as similar to this. Here also it is on three variables. Here also, of course, on three variables. But here the property, consensus property, not possible for us to use. To use the consensus property among these three terms, we need to have a specific relation. The specific relation, as per this, the observation is, while taking a term as a reference term, we need a second term in which one of the literal of the first must be complemented. Second literal must be new from the first term, second literal. If there is any third term which is coming from the first two terms, second literals, such third term is possible to eliminate. So it is observation. So that whenever in the given expression we are having many terms, among the many terms, if at all we are having many terms, among the three terms we are having possibility to apply the consensus property. To apply the consensus property among those three terms, that is the relation what we are looking, what is required. If such a relation is identified among the three terms, then of course the third term is eliminated. So based on this, if you look here, it is straightforward. Directly we are having here three terms after eliminating the first. So if you name it is a reference term, this I can name as second term because one of the literal is complemented, and I am having third term which is coming from the first two terms, second literal, so that this is the redundant term we are having possibility to eliminate. Hence, it is xz or with x bar y. It is a result. In the practice, you must be in a position, as and when we are having such two sum terms, you must be in a position to read directly while taking and between the first and last literal and between the middle two literals. Such a practice is expected to cut down the time. It is possible, you can do, not any big thing here involving. That needs little practice. It demands little practice, nothing else otherwise. The deal of this expression is xy r with x bar z is equal to x or z and with x bar or y. It is a dual of this expression. Okay, let us come to the next property. This is the last property. A or B or C or and so on is equal to A complement and with B complement and with C complement and so on. The deal of this is, A or B or C whole complement, The deal of this is A, B, C and so on whole complement is equal to A complement or B complement or C complement and so on. The name of this property is De Morgan's property. The De Morgan's property is nothing but taking complement on the given Boolean expression. De Morgan's property is nothing but taking complement on the given Boolean expression. With the De Morgan's property, what changes we are having based on the property? If you look, as similar to the dual operation, we are having interchanging of this or and operation. We are having interchanging of or and operation. And we are looking here, every literal is complemented. Every literal is complemented. So once we are speaking every literal is complemented, default meaning there is an interchanging of the Boolean constant 0 and 1. So with the dual operation we are having, with the De Morgan's operation we are looking, these are the three changes. Whereas with the dual operation we are having only the first two changes. All these three changes we are having with the De Morgan's property. Only first two changes we are having with the dual operation. Based on this, dual is subset of the De Morgan's property, or equivalently we can speak the De Morgan's property is superset of dual. De Morgan's property is superset of dual. One extra operation we are having in the De Morgan's property. The basic difference is in the dual operation there is no effect on the literal. In the De Morgan's property there is effect of the literal. So literal is complemented. So these are the changes what we are having. On the whole, these are the different properties what are possible to list on these basic operators. These are the few important properties we'll be using very frequently, and those are basically on these basic properties. Let us try a small question related with the De Morgan's property on the same given Boolean expression what we tried for the dual operation. Let us try here the De Morgan's result for this given Boolean expression. The De Morgan's result of the given Boolean expression is here also we need to look the De Morgan's operation from innermost parenthesis. So this is the innermost parenthesis. Every literal is to be complemented. So C complement R becomes and, D complement R with E. This and becomes R. Every literal is to be complement. This and becomes R. So this is the De Morgan's result of the given Boolean expression. So on the given Boolean expression, same Boolean expression, this is the dual result, this is the De Morgan's result. While looking to this dual and the De Morgan's result on the same given Boolean expression, quickly we can able to speak. While knowing the dual result of the given Boolean expression, we are having possibility without any much work the De Morgan's result, or vice versa. While knowing the dual of the given Boolean expression, to read the De Morgan's result, simply we are taking complement on every literal. Simply while taking complement on every literal, we are having here. See, something went wrong. Quickly, let's see. So this C complement and with D complement R with E, R with B, R with A complement. Things instead of referring to this somewhere in between, we refer to this. There is a thing why we are having a wrong. So anyway, it is now the De Morgan result is A complement R with B, R with C complement and with D complement R with E. So from the given Boolean expression, if you know the dual result, from this dual result we can read the De Morgan result just simply taking the complement on every literal, or vice versa. While knowing the De Morgan result, we can read the dual of this given Boolean expression taking the complement of this. So small change we are looking between the dual and the De Morgan's result is every literal is complemented in the De Morgan's operation, whereas the literal is not affecting in the dual operation. There is a small difference, difference we are looking between the dual and the De Morgan's results. Okay, let's try few more questions. Again, let us try a few simple questions first. Simplify the given Boolean expression. Simplify the given Boolean expression. Suppose expression we are having A, B are with A, B are with A complement, B are with A, B complement. So if you want to have the simplification on this, it is a given Boolean expression. So what we are looking is, among the first two terms, B is common. So within the parenthesis, it is A or with A complement and with A, B complement. By using the fourth property, what we listed there, by using fourth property, it is possible to look, it is 1. By using second property, it is possible to speak 1 and with anything is anything. Anything is here B. Because effectively B and with 1. So it is B. B are with A, B complement. Again, we are looking here using distributivity. Basically, ninth property. We are looking, this is coming as B are with A. Because we are looking here, B are with A and with B are with B bar. So this is resulting as a 1. So 1 and with anything is B or A or A or B. So answer to this question is simply A or B. It is the answer to this question. Let's look to the question. Simplified form of the given Boolean expression. X complement or Y bar Z or with XZ. Some ABCD options are given. In fact, it was the question in 1997 GATE exam. It was a question. So when we are having such a expression and the question is to identify the which is the right answer when it is simplified. To work out on this question, definitely we are in need to use the properties what we learned. What we discussed till now, those properties we need to use. It is possible to group the first and last term. We are grouping the first and last term using distributivity, using basically this distributivity property. So using distributivity property while grouping those two terms, we are having this is X complement or Z. So how it is, we can understand using distributivity X complement or with XZ. On these two terms, we are having the usage of the distributivity. Hence, this is giving X complement R with X and with X complement or Z. X complement R with X will be 1. So 1 and with anything is anything. Anything is X complement or Z. So we are having the usage of the properties what we learned till now. So that's the thing what I said. This is a role of these properties. It's a work what we are having using these properties. And let us keep the second term as it is at this point. It is Y complement Z. Again, we are looking here among these two terms after this modification. Among these two terms, we are having possibility to take Z as a common. Hence, directly we must be in a position to speak it is Z. Basically, we are having again the usage of the ninth property. Using the ninth property, we are looking here Z R with Y complement Z. Z comma Z common 1 R with Y complement. 1 R with anything based on third property, it is 1. 1 and with anything is anything. Anything is Z. But all that work we must eliminate, we must avoid basically. With the knowledge of these properties, We have to read directly like this. If you manage the time like this, definitely we'll be having proper time, enough time to perform well in the exam hall. So it needs little practice, not any complex thing involving. Only little practice will make you to do these things little fast. Anyway, from the given options, if you check, the matching answer is option C. Okay, let's go to the next question. If f of xy is equal to x complement ry, then f of x or y comma z is. Some options let us consider here. X, y bar or z, B, x complement y or z, C, x or y bar z, D, none of the above, suppose. In fact, it was a question, the GATE CS paper itself in 2005. It was a question. So this function is to be named as nested function. It is to be named as nested function. From the knowledge of the mathematics, we are supposed to speak it is a nested function. So inside function is f of x or y comma y. To work out the overall function result, it is required for us to know first the inside function result. So inside function is f of x or y comma y. Let me modify this. F of AB, let me speak. A complement RB. Better, because I am using both the places XY, you may have a little confusion, better to use this wording. So f of AB equal to A complement RB. Then f of x or y comma z is. Then we can speak this is A, this is B. By using the definition, we are speaking here, the result is x or y complement R with y. So this will result x complement y complement R with y. Of course, to evaluate this, we are having the usage of this De Morgan's property. By using this 12th property, we are able to speak it is x complement y complement R with y. Now, among these two terms, we are having the possibility to use the distributivity. With the help of the distributivity, we are speaking this result is x complement or y. So every time, no need to expand this. With the practice of the distributivity, we are supposed to be in a position to read the result like this. Anyway, for clarity, here I am giving x complement y complement R with y. It is giving x complement or y and with y complement R with y. This by using fourth property 1 and with anything, using second property, it is anything is x complement or y is the result of what I mentioned here. Now, if you come to the overall function evaluation, so this function, inner function, possible to replace as x complement or y, and of course z as it is. Now, based on the definition, what we are looking at the problem statement, this is A, this is B. Hence, we are looking this as x complement or y complement R with Z. Using again De Morgan's property, that is a 12th property, this will be x y complement R with Z. So let us check what is the matching answer. The matching answer we are having is option A. So answer to this question is option A. So what we are looking is to work out on this question, basically the properties what we learn we need to use. So this is basically the usage of the properties. This is the reason why we supposed to learn properties. The reason why we need to practice well these properties. The practicing properties is nothing but while solving the problems, you come across the usage of the property, that itself it will make you to practice, to familiar, basically to get familiarity. So let us try for one more question. If x star y is equal to x complement or y and z is equal to x star y, then z star x is equal to there are some options consider as x or y bar, b x, c y, d, none of the above. Some options I mentioned here. In fact, it is also the question for the previous GATE paper. Of course, it was a question in the CS paper in 97, 23 years back, you can say. It was a question in the GATE CS paper itself. Here he is mentioning some he is defining some operator. This operator is naming a star operator. X star y is equal to x complement or y. And also mention z is equal to x star y. Then he is asking z star x is equal to is a question. So if we look to the solution to this, let us evaluate this z star x. Z star x will be based on the statement what is available in the question. It is z star x is z complement r with x. And the definition for z is available in the problem statement as x star y. It is nothing but x complement or y. For z complement, of course, using the 12th property we are looking here, that is the De Morgan's property, x y complement. Hence, in the place of this z complement, we are substituting x y complement, and of course this literal x is coming as it is. Now among these two terms, x is common, or other way we are having possibility to use the 9th property. So based on this, the answer is x. Hence answer to this question is option B. So till now, what are the problems I discussed? To work out all these problems, we are looking to the usage of these properties to just get familiarity, just to show the usage of these properties and not remove these properties from the board. What are the problems we discuss? They are little simple problems, easy problems with lesser number of terms. We are looking to the expressions. Let's try now few little lengthy problems. Of course, the problems what we are going to discuss here also we are need to use these properties. So let's take the question as simplify the given Boolean expressions using Boolean algebra properties. Simplify the given Boolean expressions using the Boolean algebra properties. V are first one. V are with V complement W R with V complement W complement X R with V complement W complement X complement Y R with V complement W complement X complement Y complement Z. Next problem. A B complement R with B C complement R with A C complement R with A complement C R with B complement R C. Here I given some expression. A B complement R with B, C complement R with A, C complement R with A complement C, R with B complement C. Okay, so we want to do the simplification of these Boolean expressions using properties. If you try properly, without looking to my work, if you try properly, we are having possibility to read the answer to the first question is V or W or X or Y or Z. The answer to the first question will be this: V or W or X or Y or Z. We are having possibility to read the answer to this question just with the 4 steps. To answer this question, no need to fill the top to bottom of the page. No need to fill. We are having possibility to speak the answer to this question just with the 4 steps. Of course, while using properties effectively possible like this. Similarly, the answer to this question, second question, possible to read. In fact, without any work, possible to speak the answer to this question is 1. Of course, to speak this as the answer, we need to use the properties what we learned, what we listed. Such familiarity you will be getting while solving problems. So just observation, just noting is not enough. yourself you need to experience. So yourself you need to experience to use the properties so that you can do while solving many problems. While solving many problems, don't look the work conventionally, don't try with the conventional work. Possible extent, try to use the properties. You will be getting familiarity with the properties. With the help of these properties, you can cut down the paperwork. So let me try now the solution to the first question. In the first question, we are looking from second term to the last term, V bar is common. From second term to the last term, we are reading the literal V bar is a complement. Hence, the first question we are talking, once V bar is common, we are having VR with V complement within the parenthesis. This is W, R with W complement X, R with W complement X complement Y, R with W complement X complement Y complement Z. So while taking the V bar as a common in the parenthesis, we are looking as WR with W complement X, R with W complement X complement Y, R with W complement X complement Y complement Z. If you look to the distributivity, we are having from the distributivity one of the property AR with A complement B as equal to A or B. Think probably in our list I given this may be as a seventh property. If you look to the notes or if you look to the previous recording video. So AR with A complement B is A or B. Based on this, you are looking here. This total parenthesis let us consider as B. Just for our convenience, let us name it is A. This is A complement. Hence, using this property, we are reading as V or this total parenthesis. B is total parenthesis. We are looking again within the parenthesis. From second term to the last term, W bar is common. Hence, while taking the W bar as a common, within the parenthesis, this is X or with X bar Y or with X bar Y bar Z. Again, we are having possibility to use this distributivity property, that is seventh property, what we listed. So while using the seventh property, this will be now V or W or this total parenthesis, that is X or and so and so. Again, we are looking among these two terms, X bar is a common, so Y or with Y bar Z. If you repeat the same property among the last two terms here, this will be V or W or X or within this, if you apply the same property, Y or Z. So, answer to this question is V or W or X or Y or Z. To read the answer for this, such a lengthy expression, we are looking just usage of 4 steps. We are having the usage of only 4 steps, and of course, we are using basically distributivity. While having the knowledge of this distributivity, repeatedly using the same distributivity property, we are looking to the final answer just with the 4 steps. Instead of working like this, we are having possibility to read the answer to this with alternative groupings also. With alternative grouping also, you may read the answer. But definitely if you try with alternative grouping, I am sure your answer will exceed more than 4 steps. So somebody is working the solution with 4 steps, somebody is taking more time to work. Definitely, as far as the exam hall is concerned, he is the student who is working with less time, less paper. Less time is because the less paperwork basically. So the somebody is working with less paperwork, he is a student, he is getting the benefit. So majority may be answering to this question. The students, those who are answering to this question with less time, those students will be having a benefit as an overall performance of the exam. Okay. So similarly, let's come to the next question. The next question answer also I said already, the answer must be 1. And we can speak the answer to this question I said without any work, without any paperwork I said. We can speak the answer, or if at all it is a multiple choice, one of the option will be 1. So that answer we can pick without any paperwork, it is possible. And if you look here how it is so. If you group the last two literals, by using De Morgan's property, that is a 12th property what we listed, it is BC complement whole complement. In the same expression I am having this BC complement. If we speak this BC complement is X, then definitely this term I suppose to read as X complement. Hence, I am looking in the same expression, this X and this X complement, they are related with the OR operation. If I am having such a case, no need to look to the other terms, no need to bother about the other terms. When I am having in the same expression X and X complement, they are related with OR operation. Using fourth property, we know X OR with X complement is 1. So 1 OR with anything, using third property, we know it is 1. So that to pick the answer to this question, no need of any paperwork. Directly we can pick the answer like this. Let us try one more question. Same simplification. Simplify the given Boolean expression . So let us take the question. Simplify the given Boolean expression. The Boolean expression is A C complement R with B complement D and with A complement D, R with B D complement and with C or A B complement. For this portion, it is a complement and overall complement. Overall complement, the square bracket. So we want the simplification on this Boolean expression. Whenever the given Boolean expression is having like this more than one complements, my suggestion is first try to evaluate innermost parenthesis. Try to evaluate first innermost parenthesis or innermost complement or parenthesis. Okay. After evaluating the innermost, let us substitute. Basically, the work what I want to suggest you is when we are having a expression something very lengthy with many brackets, there is many parentheses and many complements. Try to look at the problem piecewise. Do the simplification piecewise. Later you substitute the results. It's the best way to work out on this question. So if that's the case, I will evaluate first this expression B D complement and with C or with A B complement whole complement. This term I will evaluate first. So if you evaluate first this, if you evaluate inside this complement, we are looking here, this is BCD complement. BCD complement. Other term is here B complement. So it is 0. So B and the B complement while evaluating, it becomes 0. For if you want clarity, I will write here A, B, B complement, D complement. But really speaking, we must avoid this. Anyway, this is 0. Then I am having this as B, C, D complement, whole complement. Now let me come to this term. If you come to this term, outside B complement D, inside we are looking to the square bracket. One term is A complement D, other term is B, C, D complement, whole complement, and of course we are looking here, this is complemented. The square bracket is complemented. So square bracket is effectively coming to be A complement D or with B, C, D complement, whole complement. While evaluating this B complement D outside, this inside A complement D complement, and this is B, C, D complement effectively, because we are looking B, C, D complement, already one complement and one more complement. And of course, this R becomes INT. This R becomes INT. Hence, if you look here now, B complement D, this is B. So when I am having B complement outside, B inside, B complement becomes 0. So I can write directly, this becomes 0. Once this is 0, then the answer to this question will be AC complement. Answer to this question will be AC complement. So like this quickly we can speak. If you want in detail work, if you want the detail work, it is to be now B complement D, and inside this, by using De Morgan's property evaluating, it is A or D complement and with B, C, D complement. Okay, so B complement D, here one term is A, B, C, D complement, other is B, C, D complement. So finally it is same. If you evaluate here B complement, here B, among these some terms will be there. Similarly B complement B, and of course D also there, that are also producing. Finally it is coming to be 0. So what I mean to say is, whenever it is reduced something like this, immediately we must be in a position to recognize this result is 0. Such thing we can recognize with only practice, not any shortcut things, not any easy way, not any shortcut, or not any ready-made thing, not any formula type of work. It needs only your practice. With your experience, with your practice only you can speak this is 0 with less time. Anyway, the answer to this question is AC complement. Let us go to the next question. The next question is, find the values of Boolean variables. Find the values of the Boolean variables A, B, C and D while solving following Boolean equations. While solving the following Boolean equations. So the Boolean equations are A complement R with AB is equal to 0, A B complement is equal to AC, AB R with BC R with CA is equal to CD complement. So the question what we are looking is, we want to identify the values of the Boolean variables A, B, C and D while solving these equations. It is a question. We are having 4 variables. These 4 unknown variable values, Boolean variables basically, we need to identify by using these 3 equations. Let us name it as equation 1, it is equation 2, it is equation 3. While solving these equations, we need to identify the values of the Boolean variables A, B, C and D. So if you look to the solution, by using distributivity, the equation 1 possible to simplify as A complement R with B equal to 0. By using distributivity, the equation 1 when we simplified, it is nothing but A complement R B. If you want detailed work, of course, as I said, we need to avoid, but anyway, for clarity, I am putting here this A complement R with AB using distributivity. A complement R A couple of times, earlier problems also we use this sort of things, so it should not be any problem. So this is 1 using 4th property, effectively it is A complement RB. So A complement RB is equal to 0. This result will be true if and only, this result will be true if and only A complement is 0 and B also 0. To get A complement is to be 0, A must be 1. Because they are the binary variables. This equation result is to be 0 means B must be 0 and A complement must be 0. A complement 0 possible if and only if A is 1. Hence, A is 1, B is 0. While substituting AB values in this equation 2, we are looking here, A is 1, B complement is 1, A is 1, C unknown. So LHS is 1. This 1 is possible if and only if the C is 1. This equation is possible to as a true if and only if the C is 1. Now while substituting ABC values in the equation 3, we are looking A is 1, B is 0, C is 1, A is 1, C is 1, D bar unknown. So LHS is 1. That is possible if and only RHS D bar is 1. So to get the D bar is to be 1, D must be 0. To get the D bar is to be 1, D must be 0. So that while solving these Boolean equations 1, 2, 3, we are reading the values of the Boolean variables A, B, C and D are 1, 0, 1, 0 respectively. Here, one interesting point we need to understand. There are 4 unknown variables. To identify these 4 unknown variables, available equations are only 3. By using these 3 equations, we are finding 4 unknown variables. If at all the similar question we are having in the normal conventional algebra, to find 4 unknown Boolean variable values, we are in need of 4 equations. But that is not the case in this Boolean algebra. The reason is very simple. In the case of the conventional algebra, the variables are not binary variables. Variables are decimal variables. The conventional algebra is depending upon the decimal number system. The t is base of 10. Whereas the Boolean algebra is based on the binary number system, that is a base as 2. So because of this, variable may be having maybe 0, maybe 1. If B is not 0, B must be 1. No any other value. Suppose I am speaking a variable x is a Boolean variable. X value is not equal to 1. Then guarantee as a Boolean variable x value must be 0. Such a thing we are not having guarantee in the conventional algebra. It is the reason why we are finding 4 unknown Boolean variable values just by using only these 3 equations. It may be possible, of course, Based on the equations, it may be possible. Using only 2 equations, finding 4 unknown Boolean variable values, it may be possible, of course, based on the equations. So all these are possible here basically because it is depending upon the binary number system. It's a reason. Consider f is a Boolean function on the variables x, y, z. X is a Boolean function on the variables x, y, z. And this function is given as x, y bar r with x complement y r with x complement y z complement. Let us name this is equation A. So we are talking here f is a function on the Boolean variables x, y and z. As long as the variables x, y and z are the Boolean variables, the function f is named as Boolean function or switching function. As long as x, y and z are Boolean variables, the function f is named as a Boolean function or switching function. We consider this Boolean function or switching function is having the representation as x, y bar r with x bar y r with x complement y z complement. This form of expression is named as sum of product form, where the word sum is referring to or operation. The word product is referring to and operation. The word product is referring to and operation. Similarly, let us name other function, say f2. Let's name the previous function as say f1 just to distinguish from the previous. f2 of ABC. As and when the variables ABC are the Boolean variables, as and when the variables ABC are the Boolean variables, the function f2 also named as a Boolean function or switching function. Consider this Boolean function or switching function is having the representation as A complement or C and with B or with C complement and with A or B complement or C complement. This form of expression is named as product of sum form. This form of expression we are naming as product of sum form. When the expression is in the sum of product form, or when the expression is in the product of sum form, how to develop the truth table? How to develop the truth table for this maybe SOP expression or POS expression we already discussed. We already discussed how to develop a truth table. If you rewind your video and if you check, while giving the proof of distributivity, we come across this. While giving the proof of the distributivity, we are looking the usage of developing the truth table for a SOP expression or POS expression. You can see it is there on the board. I not removed basically to use this. So LHS expression was A or BC. It is SOP expression. It is SOP expression. Similarly, RHS expression was A or B or with A or C. So it is basically POS expression. So that is the thing what I said. We already covered, we already know how to develop a truth table, how to develop a truth table, maybe for a SOP expression or maybe for a POS expression. Now let us take the problem in reverse. Now, if at all we are looking a function f, consider a function f. It is defined in the truth table like this. It is defined in the truth table as like this. It is a function on the variables a, b, c, and the truth table of the function is this. Now we need to take the question, or we need to take the problem as, what is the SOP expression, what is the POS expression for the function f which is defined in the truth table. It is a reverse to the work what we had earlier. While giving the proof of the distributivity, the work what we had, it is reverse to that. So let us take this as the question. So note down. The function f of ABC is defined in the truth table as shown below. The function f of ABC is defined in the truth table as shown below. Write a bit. Write a bit. SOP expression for the function f of ABC. Write SOP expression for the function f of ABC. B bit. Write POS expression for the function f of ABC. So it is the question. Let us try first for the SOP expression. Later we'll try for POS expression. So to write the SOP expression of the function, we need to refer to the combinations where the function output is 1. Better note down. From the truth table, when we want to read the SOP expression, the first point is refer to only those combinations of the truth table. Refer to only those combinations of the truth table where the function output is 1. Where the function output is 1. If you come to the question what we are having here, we are looking here, these are the 4 combinations where we are having the function output is 1. One combination is 0, 0, 1. Next combination is 0, 1, 0. Third combination is 1, 0, 0. Fourth is 1, 1, 0. For these 4 combinations, we are reading the function output is 1. So while referring to these combinations where we are having the function output is 1, we are coming to the second step. The second step is reading such product forms. Reading such product forms for each one of the combination. Here the product is nothing but AND operation in the Boolean algebra, and sum is nothing but OR operation in this Boolean algebra. So we need to read such product forms for each one of the combination where we are having the function output is 1. So to read the product terms, the rule what we are having is, better note down. The rule what we are having is, better note down. If the variable is having, if the variable is having the value as 0, it is present in the product form. If the variable is having 0, it is present in the product form with a complement. Otherwise, it is present in the product form. Otherwise, it is present in the product form without complement. Otherwise, it is present in the product form without complement. So it's a statement. So if the variable, in general I am talking, x is 0, it is present in the product form with a complement. If the variable x is 1, it is present in the product form without complement. It is a rule we need to follow to read the product form. So based on this rule, let us try now to read the products for each one of the combination where we are having the function output is 1. For this combination 0, 0, 1, product is possible to read as A complement, B complement, C. Because we are looking A and B are with a Boolean constant value 0. So on A and B we are having complement operation. C is the Boolean constant of 1. So C is on complementary form. The next combination we are looking 0, 1, 0. That will be A complement, B, C complement. And so on, like this we need to list. The next one will be A, B complement, C complement. The next one is AB, C complement. So like this we are reading the products for each one of the combination where we are having the function output is 1. Later we are coming to third step. The third step is taking OR operation among all these product terms. While taking OR operation among all these product terms, this will be f of ABC is equal to A complement, B complement C, or with AB, or with A complement B, C complement, or with A, B complement, C complement, or with AB, C complement. Let us name this as the equation 1. So this equation 1 is very similar to the equation A. Once it is very similar to the equation A, we must name this equation as sum of product form. We must name this equation as SOP form, sum of product form. Till now, we were discussing some properties. Using properties, here we are having possibility to do the simplification. Here we are having possibility to do the simplifications using properties. We are having possibility to group this second term with the last term. While grouping the second term with the last term, we are having a product is BC complement, or basically we are having elimination of the variable A. So to read this product, basically we are using one of the property what we learned earlier, or the properties what we learned earlier, those things basically we are using. We are looking among the second and last term, BC complement is a common. Hence, within the parenthesis, it is A complement or with A. Using fourth property, this is 1. Using second property, 1 and with anything is anything. Anything is BC complement. Okay. Just think any further grouping is possible. Just think any further grouping is possible. Answer to my question must be yes, further grouping is possible. I was mentioning a question, any further grouping is possible or not. I am asking you to check the answer to this question with an observation. You need to speak as further grouping possible. Further grouping is possible among the last two terms. Don't be in a hurry to come to a conclusion. जल्दी में conclusion नहीं आना. Last term I already grouped with the second term, and don't ask me why we are grouping these last two. Yes, it is possible. I will speak how it is possible later. But don't be with a wrong conclusion. Quickly wrong. Don't come to the conclusion. Not allowed. It is allowed. Why it is allowed? I am giving some time. In the meantime, you think I will speak how it is allowed little later. It is possible to group even the last two terms. If at all we are grouping the last two terms, it will be AC complement. If you group the last two terms, it will be AC complement. Same, I am having AC complement as a common. So within the parenthesis, I am looking B complement or B. So while taking AC complement as a common, within the parenthesis, it is a B complement or B, that is 1. So 1 and with anything is AC complement. The first term not possible for us to group with any other term. So first term we suppose to read as it is. Let us name this as equation 2. It is also similar to the equation A. Hence, we must name even this equation 2 also as SOP expression. We must name the equation 2 also SOP expression. Now, I will speak how we are using this last term to group this second as well as third. I will speak. Just refer to first property. Rewind your video or look to your notes. Look to the first property. The first property was, I am using maybe other variable XR with X any number of times. It is X. In other way, X, if at all I am looking once, I can write if I want twice with R operation. If I want, I can write thrice with R operation, or like this, I can write any number of times. It is logically allowed. It is the first property. So based on this I can speak the last term as say X. If I speak as a X, I am using it X twice. So logically it is allowed. But it is very true. The same thing is not possible in the conventional algebra. Same thing is not allowed in the normal conventional algebra. But in this Boolean algebra, it is allowed. Based on the first property you are speaking, it is allowed. The first property was basically with the truth tables what we develop. 1 R with 1 any number of times 1, 0 R with 0 any number of times it is 0. Based on this generic expression we mentioned as XR with X any number of times is X, or X is present once means we can write if it need XR X or XR 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 X like this. So basically by using first property we are speaking this. It is back to these equations. The equation 1 and equation 2, equation 1 and equation 2, both are SOP expressions. But there is a speciality in the equation 1 while comparing the equation 2. The speciality what we are having the equation 1 is, in the equation 1, all the products we are reading with all the variables of the given function. All the products we are reading with all the variables of the given function. Whereas in the equation 2, that is not the scenario. At least the second and third term, we are not looking with all the variables. Maybe first term is available. But in the equation 1, every product we are reading with all the variables of the given function. Hence, to distinguish the SOP expression 1 from SOP expression 2, we are giving a new name to the SOP expression 1. The new name what we are giving to the equation 1 is canonical sum of product expression. canonical sum of product expression. We are giving a name for the equation 1 as canonical SOP expression. So that in the canonical SOP expression, we'll be having the products with all the variables of the given function. In the canonical SOP expression, we'll be having the product terms with all the variables of the given function. Variable may be complementary or uncomplimentary form. So in other way, a SOP expression, if we want to speak as a canonical SOP expression, in that we need to look all the products must be with all the variables of the given function. Then only that expression we suppose name as canonical SOP expression. And each one of the term in the canonical SOP expression must be named as, each one of the term in the canonical SOP expression must be named as min term. Each one of the term in the canonical SOP expression must be named as min term. So now we need to define this new word min term. Note down. Min term is a product term. Min term is a product term. It contains all the variables. Min term is a product term. It contains all the variables. If I stop the statement of the min term with this wording, try to speak, try to check the statement what I mentioned with this wording. Is it giving full meaning for the definition of the min term? Is it giving complete meaning for the definition of the min term? Try to check. The statement what I mentioned is min term is a product term. It contains all the variables. With this I stop. If at all I am stopping the statement with this, it is giving full meaning for the definition of the statement. The answer from your side, from your end, supposed to be no. It is not giving full meaning for the definition of the min term. The reason is we are not naming this combination product is a min term, or this combination or this combination or this combination. We are not naming these combination products as a min terms. We are naming only these combination products as a min terms, where we are having the function output is 1. Where we are looking to the function output is 1. So every combination we are not naming as a min term. If somebody asks, this is a min term, your answer is supposed to be no, it is not a min term. Where we are having function output is 1, such combination products only we are naming as the min terms. Hence, the complete definition for the min term is, we need to continue further as, we stopped here, min term is a product term which contains all the variables. Later we need to continue as, for that combination, the function output must be 1. For that combination, the function output must be 1. So full complete statement is, min term is a product term which contains all the variables either complementary or uncomplimentary form. For that combination, the function output is 1. Min term is a product term which contains all the variables either complementary or uncomplimentary form. For that combination, the function output must be 1. So total possible number of min terms on these 3 variables are 8, no doubt. Total possible number of min terms, I am speaking total possible number of min terms. Total possible number of min terms, no doubt, without any doubt, you can speak as 2 to the power of n. Here n is 3, so that 8 combination. But every combination for a given function may not be min term. They are looking here the word as possible. So in every function, all the combinations may not be min terms. In every function, if at all you are looking, few of the combinations will be the function output of 1. Those combinations only will be naming as minterms. The combinations which are not with the function output of 1, they are not the minterms. Be clear such concept things. These minterms we are reading with small letters m. For a given function, we are having possibility for more than one combinations or more than one products as a minterms. To distinguish within the function these minterms, we are adding decimal subscript. We are adding the decimal subscript. The meaning of the decimal subscript we can understand easily. We are speaking here the decimal subscript is 4. The reason is very simple. For this combination of 100, the decimal equivalent value is 4. It is the reason why we are putting here the decimal subscript 4. For this combination of 0, 1, 0, the decimal value is 2. It is the reason why we are putting this is 2, and so on. Now, by using this terminology also, we are having possibility to write the expression. By using this terminology, if we write the expression must be M1 R with M2, R with M4, R with M6, or alternatively sigma M 1, 2, 4, 6. This form of expression also we are naming as canonical SOP expression. This form of expression, let us name 1 dash. This is also named as canonical SOP expression. It is also named as canonical SOP expression. Again, to distinguish between 1 and 1 dash, this 1 supposed to be named as expanded canonical SOP form. Whereas 1 dash we are naming as compact canonical SOP form. 1 we are naming as expanded canonical SOP form, whereas 1 dash we are naming as compact canonical SOP form. Now, as similar to this, we must try for the B bit. The B bit I mentioned, we want to write the product of some expression for the function f, which is given in this truth table. So B bit POS form. Earlier it was A bit SOP form. So with the knowledge of the SOP, we can talk quickly about this POS expression. Here we are referring to the combinations where the function output is 0. We need to refer to the combinations where the function output is 0. Earlier we referred to the combinations where the function output was 1. Here we are referring to combinations where the function output is 0. So for the given Boolean function, we are looking, there are 4 combinations which are with the function output of 0. They are this combination 0, 0, 0, 0, 1, 1, 1, 0, 1, the last combination 1, 1, 1. These are the 4 combinations we are reading here with the function output of 0. After identifying the combinations where the function output is 0, the next task is reading the sum terms. Next task is reading the sum terms for each one of this combination. So we need to read such sum terms for each one of the combination where the function output is 0. To read the sum term, the rule what we are having is, if the variable is having the value as 0, it is present in the sum term without complement. Or if the variable is having the value as 1, it is present in the sum term with a complement. So more or less we are having a little reverse work of SOP. In the SOP case, whenever the variable is having the value as 0, it is present in the product term with a complement. When the variable is having the value as 1, it is present in the product term without complement. Here, whenever the variable is 0, it is present in the sum term. It is not product term. Now it is sum term. Sum is OR operation. It is present in the sum term without complement. With a value of 1, it is present in the sum term without complement. So by using this rule, let us read here the sum terms. For first combination, ABC or 0, 0, 0. Hence, this will be A or B or C. For next combination, 0, 1, 1, the function output is 0, A, B complement or C complement. Here, B and C are 0, 0, B and C are 1, 1, so that on B as well as C we are looking complement. A is 0, A on complementary form. In the first case, all the variables are 0, so we are looking simply A or B or C. And so on, if you work like this, this will be A complement or B or C complement. The last one will be A complement or B complement or C complement. Now, we need to take AND operation among all these sum terms. We need to take AND operation among all these sum terms. So, if we write AND operation among all these sum terms, the expression is F of ABC, A or B or C, and with A or B complement or C complement, and with A complement or B or with C complement, and with A complement or B complement or C complement. Let us name this as equation 3. We are looking this equation 3 is similar to the equation B. Once the equation 3 is similar to this equation B, we must name the equation 3 as product of some expression. So, this equation 3 is product of some expression. Here also, we are having possibility to do the simplification on this equation 3 using properties. Here, using properties, of course, whenever we are working simplification using properties, the work is coming to be effectively, while grouping the terms, we are minimizing, we are simplifying basically. That is the work what we are having. Here, we are having possibility to group this second term with the last term. Keep attention. We are having a possibility grouping of the second term with the last term. While grouping the second term with the last term, possible for us to read a sum term as B or B complement or C complement. Possible to read the sum term as B complement or C complement. And of course, the variable A is eliminated. If you take a question, by using which property we are having this result, the answer to this question from your end supposed to be using distributivity. Here you can see in both these sum terms we are having this B complement, C complement. Just for our convenience, this I speak as say X. Then I am having the second term is A or X. The last term is A complement or X. Using distributivity, this will be X or with A complement. If you look to the distributive property, that is resulting to be this. This AA complement is 0. using fourth property, the leftover is only x, where x is b complement or c complement. Hence, while grouping the second term with the last term, we are having a sum term with the elimination of the variable a is b complement or c complement. Similarly, think any further grouping possible in this equation 3. Any further grouping is it possible in this equation 3? Let's try to think. The answer to this question must be yes. The answer to this question must be yes. We are having further grouping also possibility here. Further grouping is we are having possibility to group the last two terms. If you group the last two terms, the sum term will be a complement or c complement. We are looking a complement or with c complement is a common in the third as well as fourth term. So that as similar to the earlier work, grouping of the second and fourth term, as similar to the earlier work, we are looking here, the result is coming to be a complement or c complement. So don't get confused. It may be a repetition, but don't get confused. As similar to the SOP case, here also we are working. This last term we are using to group the second term as well as third term. It is allowed. It is allowed basically the property what we learned. It is allowed basically the property what we learned. That is the first property. The first property was x is equal to x and with x, or x is equal to x as many times as you want. You can take the and like this. So that is the rule what we are having the usage. Of course, the first term not possible to group with any other term. So let us keep the first term as it is. Let us name this as equation 4. Equation 3, equation 4 both are similar to the B, the initially what I said. So both are basically POS expressions. So equation 4 also we supposed to name as product of some expression. So quickly let us speak now with the knowledge of SOP work. There is a clear difference between the equation 3 and equation 4. There is a clear difference between the equation 3 and equation 4. The difference is, in the equation 3, all the sum terms we are looking with all the variables the given function. Whereas the equation 4, we are not reading all the sum terms with all the variables. Of course, first maybe with all the variables, but the second and third are not with all the variables. But it is not the case in the equation 3. In the equation 3, we are looking all the sum terms are with all the variables the given function. Hence, to distinguish equation 3 from the equation 4, we supposed to name the equation 3 as canonical product of some expression. We suppose to name the equation 3 as canonical product of some expression. Hence, in the canonical product of some expression, all the sum terms we suppose to read with all the variables of the given function. Maybe variable complementary form or uncomplementary form, that is a different issue. So, if you look to the definition of the canonical product of some expression, any POS expression we are naming as a canonical product of some expression if and only in that expression every sum term is with all the variables of the given function, then only we are naming it is canonical POS expression. So every POS expression may not be canonical POS. To name a POS expression as a canonical POS, it is a rule it's supposed to follow. Each sum term in the canonical POS expression must be named as max term. Each sum term in the canonical POS expression must be named as the max term. So that now we need to define this max term. With the knowledge of the min term, we can speak quickly the definition for the max term. The definition for the max term must be max term, better note down, max term is a sum term. It contains Maxsum is some term, it contains all the variables either complementary, it contains all the variables either complementary or uncomplementary form. It contains all the variables either complementary or uncomplementary form. For that combination, the function output must be 0. For that combination, the function output must be 0. So it is the definition of the maxterm. So maxterm is some term, for that combination, the function output must be 0. So as similar to the minterm, every combination is not a maxterm for the given function. Which are the combinations for which the function output is 0? Only those combinations must be named as maxterms. In this question, we are looking, there are 4 maxterms. This is M0, this will be M3, this will be M5, this will be M7. So maxterms we are representing with the capital M and decimal subscript. Of course, the meaning of the decimal subscript is similar to the minterm case. So we are looking the decimal subscript for this as a 5. The reason is for this binary combination equivalent decimal number is 5. Hence, you can speak now total possible number of maxterms. Total possible number of maxterms on a function of n variables is to the power of n. Whenever n is 3, total 8. These are the maximum number of possible, total possible number of maxterms. Maximum number of maxterms or maximum number of minterms. But we know every combination may not be minterm or every combination may not be maxterm on the given function. There are some combinations with a function output of 0. They are the maxterms. There are some combinations with the function output of 1. They are the minterms. So these are only talking total maximum possible number of minterms or total possible number of maxterms. So every combination on the given function may not be minterm, may not be maxterm. By using this terminology, it is possible to read the expression as M0 and with M3 and with M5 and with M7. Or alternatively, we can read pi M of 0, 3, 5 and 7. This form of expression also we must name as canonical POS expression. So definitely with the knowledge of our earlier SOP, we are speaking this 3' as compact canonical POS form, whereas the equation 3 we must name as expanded canonical POS form. So these are the procedures to write the SOP expression. These are the procedures to write the SOP expressions and the POS expressions whenever the function is given in the truth table. As and when the function is available in the truth table, by using these procedures, we are reading the SOP forms and POS forms.